Excuse me. Hello and welcome to chapter 5. So I was in the middle of taking a drink when I hit record. That was pretty dumb. Okay, well, hi, welcome back. It's chapter 5. We're going to talk about the Earth and its moon. So here is the Earth from the moon, taken in 1968. We're going to talk about the Earth moon system, how the moon affects the tides, some atmospheres, and some other things we're going to talk about. So we're going to summarize the structural properties of the Earth and the Moon. So we have some terms that we use to discuss planets and moons and stuff. So surface gravity is the strength of the gravitational force at the body's surface. Escape speed is related to surface gravity. It's the speed that's required for an object to escape the gravitational pull of a body. So, for instance, the smaller the body, the less the gravitational pull, and of course, then the less the escape speed that you have to achieve in order to escape the body. Okay. For geology, though, we have a few terms, which are shown on the next slide. And we have a mantle, core, crust, atmosphere, and magnetosphere. So here we have a representation of the Earth and the Moon. So if you'll notice, we've got some properties here with their mass and their radius, and then the densities, surface gravity. Escape speed is 11 kilometers per second for the Earth and 2.4 kilometers per second for the Moon. And then, of course, its rotation period, which we have 23 hours and 56 minutes. If you remember, that's the sidereal day, not the solar day. And then, of course, the moon, the rotation period is 27.3 days. But that's also, it's 29 when you think of, these are the shorter time periods, but there's the longer time period if you compare to the stars versus, no, longer if you compare to the sun. Anyway, okay. So here we have the core of, we have the inner core and then the outer core and then the mantle. And then here we have, what do we, oh, we've got crust, soft mantle, solid rocky outer core. There's been, it looks kind of like a jawbreaker, doesn't it? So there's been conspiracy theorists that the moon is hollow and it's inside there's a city or some stuff. What fun, huh? Okay. So the interior of the Earth from the inside out, we have a metallic core, we have a rocky mantle, we have a pretty thin crust, we have a troposphere, the outer, or I'm sorry, the lower atmosphere. We live in the troposphere, and then the magnetosphere, and of course tides. So this is going to explain tides. Whenever I go to the beach with my mother, she's always convinced the tide is it's getting to be high tide. She's always convinced. Okay. So tides are daily fluctuations in ocean levels. They can range in magnitude from a few centimeters to many meters. So there are two high tides and two low tides each day. Gravitational influence of the moon, the earth, and the sun cause tides on our planet, which is unique because we have so much water and it covers 3/4 of the earth's surface. So there's tidal bulge that stretches along a line that joins the Earth and the Moon. And there's this differential force, which basically means that the force is different at different levels, which we'll see, which kind of creates this tidal force. So tides are due to gravitational force on Earth from the Moon. And the force on the near side of the Earth is greater than the force on the far side. And water, of course, can flow freely in response to that gravitational pull. The opposite side, high tide, comes from the earth being pulled and then the water sort of being left behind, which is a little weird. So here we have the earth and our oceans, and then there's the moon, although this sort of looks like the moon is at the North Pole, but that's a little weird. Anyway, and so there's a different pull here versus here versus here. That's the differential part This would be stronger than at the poles. And then, of course, here we have the high tide over here on the side that's facing. And then on the other side of the Earth, the high tide is basically because the Earth is now sort of positioned. I mean, it's always that way, but it's, yeah, so this water is sort of left behind. That's their explanation in the book. I don't know. I think we should go to the beach and test it out. So the sun does have an effect, but only slightly. It's when we have a new moon or a full moon, we have a slightly higher tide. And then if we have a third quarter moon or a first quarter moon, the high tides are not as great. So the moon, full moon and new moon can have greater tides than other moons. So the tides also exert sort of this drag force on Earth, which slows its rotation a little bit. This will continue until the Earth rotates synchronously with the moon so that the same side of Earth always points toward the moon. At the moment, the moon, one side always faces us, so it'll eventually be where the two sides will face each other as they go around. And so it'll be one of those things like you'll have moon tourism where you'll have to go to the side of the moon that you can see, the side of the Earth where you can see the moon kind of thing. That should be a sci-fi movie, right? This has already happened with the Earth, with the moon, whose near side is always toward us. So if we've got a dude standing on the moon and he's looking at the Earth, even as he goes around, he will always be pointed toward the Earth. This is called a synchronous orbit. The moon spins once in its orbit when it makes one revolution around the Earth. So tidal gravitational interaction have slowed the Earth's spin to match its orbit. Earth's orbit will become tidally locked with the moon in the future. Sorry, it was the same bullet as before. That's why I got confused. Anyway, so eventually they will be locked together. All right. So the atmosphere, so the troposphere, we live in the troposphere. It goes up to about 12 kilometers, which is Mount Everest is 9 kilometers high. So most humans who are not astronauts, most humans are not astronauts. Most humans will never get out of the troposphere, even planes flying the troposphere. The stratosphere is 12 to 40 kilometers high. The ozone layer is there, which ozone is 3 oxygen atoms in a molecule rather than 2. There's the mesosphere, the ionosphere, and then this sort of like convection, or sorry, ionosphere is where partially ionized gas is trapped. And there's this convection zones, which help give us weather within the troposphere. Mm-hmm. There we go. So we'll see this sort of atmosphere cross section when we talk about each of the planets, but the blue curve shows sort of temperature at each atmosphere. At each altitude. So the troposphere is where convection will take place down here. It's also responsible for the weather. So unlike planes only fly like up in here and stuff like that. So here's the stratosphere and then the mesosphere and ionosphere. Convection is the thing that gives us weather. It depends on warming of the ground by the sun. So the sun will heat the ground and warm air will rise, and then it'll, like the cool air will come down and replace the warm air that just left. So it's sort of the convection. The ionosphere is ionized by solar radiation. It's a good conductor. It reflects radio waves in the AM range, but is transparent to FM and TV. So aliens cannot get our AM transmissions, but they can get our TV and FM. And if you are a fan of Futurama, so or Galaxy Quest, then there's aliens that watch our TV shows. The ozone layer through here also helps absorb ultraviolet radiation, which will protect life on the planet, protect your skin. Chlorofluorocarbons, sorry, CFCs, they thought they were damaging the ozone layers in the 80s or 90s, and so they were banned. And so when we first started putting satellites out and started noticing, they measured a hole in the ozone layer in Antarctica, and they thought it was CFCs that were combining with the ozone molecule, the 3 oxygen molecule, and destroying it. And so then the ozone layer started to heal, which was great. And then there's growing again. So there's some controversy or some questions about whether it was the CFCs or not, but they have different refrigerants now, so it's okay. So the sun emits most of its energy in visible and near infrared, the wavelengths that are slightly longer than red light. The Earth's atmosphere is largely transparent to radiation of this type. So almost all of the solar radiation that is not absorbed or reflected by the clouds heats up the Earth's surface. And so surface heating, sunlight that is not reflected or is absorbed by Earth's surface and warms it a little bit. The surface then sort of re-radiates as infrared thermal radiation. Then the atmosphere absorbs the infrared, causing further heating, which sounds scary. This is called the greenhouse effect. And it's kind of good, but it's also kind of something we got to look out for. So this is known as the greenhouse effect. So visible sunlight comes in, it can bounce off clouds out back into the atmosphere. It could come in and heat up the surface, and then it's re-radiated back out into space. A little bit is escapes, but some of it is actually reabsorbed. So they have carbon dioxide molecules here that are reabsorbing it. Water vapor also reabsorbs it. And we can control carbon dioxide molecules a little bit, but we cannot control water vapor. So anyway, so this greenhouse effect, though, is important for the Earth. There's an extremely strong evidence that Earth is getting warmer. The cause of this warming is subject to intense debate. Many scientists believe it is related to the corresponding increase in atmospheric carbon dioxide. This may not be true. So there's this question about global warming, and sometimes I make students mad when I'm like not a true believer in climate change, man-made climate change. Climates change, and the climate on the planet has changed multiple times. We used to be in an ice age, and now we're not. And that was before we had cars and a whole bunch of cows. So how did we get out of the ice age then? That's just my question here. There was a scandal in the 90s, I think it was, where some climate data was fudged, and they changed the climate data. There were some emails that proved that they were kind of doing this. So anyway, so here is like this carbon dioxide measurement that they have. This is from ice cores and stuff. And then this kind of, I think actually the book describes that there is a carbon dioxide atmospheric monitoring station on top of a volcano. So, I mean, it's in one spot and it's like on top of a volcano. So, and volcanoes emit carbon dioxide. So anyway, so they have this. So what they did is they don't go back in time far enough, and then they fudge some of the data. But you believe what you believe. Okay, I'm just saying that carbon dioxide absorbs the same infrared light as water vapor also. Okay, so what they're trying to teach you, though, is that in the past, carbon dioxide levels were less, and now they're greater, and the temperatures has also risen. Actually, I did see another theory that the carbon dioxide levels in the atmosphere are determined by the ocean, and then the temperatures lag the ocean's response, and so that it's not necessarily so there's this weird cycle that we don't quite understand because we've only really been scientifically measuring it for the last 80 years or something like that. So okay, so long wavelength infrared is partially blocked from being re-emitted back into space because carbon dioxide and water vapor absorb the radiation. So this partially traps the solar radiation, and it's called the greenhouse effect. It is responsible for Earth having liquid water, because if we didn't have the greenhouse effect, we would be about 40 degrees cooler. So 40 Celsius, basically cooler, which I think 70 degrees is like 20 something, right? So we would be frozen if we didn't have the greenhouse effect. So the greenhouse effect is not inherently bad. So here's the internal structure of the Earth and the Moon again. The Earth has a radius of 6,400 kilometers. We can only drill into the crust about 10 kilometers because no materials can withstand the conditions at that depth. So all of like our diamond tipped drill bits are destroyed at that depth. We developed a way to see inside the Earth, though, by studying earthquakes. I think this is totally fascinating. So seismic waves, earthquakes produce pressure waves and shear waves. So P waves, or the primary waves, or the pressure waves, they will travel through liquids and solids, but secondary waves, S waves, secondary waves, or shear waves will not travel through liquids, as liquids do not sort of transmit the shear forces. And wave speeds also depend on the density of materials. So what they did, so a pressure wave is a longitudinal wave, whereas a shear wave is a transverse wave. What in the world does that mean? A shear wave cannot propagate liquid. So here is a P wave and here is an S wave. So if you have a slinky and you stretched it out and you push the slinky and this little, the compression part will go back and forth because it's a wave. That is a P wave. If you took the slinky and you whipped it up and down, or like had a rope and did this, that is an S wave. So this will not go through liquid, but this will. So we can look at what happens when there's an earthquake where other places are registering the earthquake. And we can sort of infer different things about the core. So an earthquake occurs here and it travels through the earth and it's measured here and we see P waves and S waves. It's measured here, we see P waves and S waves. It's measured here, we see P waves and S waves. Here we only see weak P waves and no S waves. And then over here, we only have P waves. And so because this is how we know that there is a solid inner core and a liquid outer core. I hope I said that right. So the currently accepted model of the structure of the Earth is an inner core, outer core, mantle, and a crust. And this sort of shows the density where the core is much more dense. And then, of course, the temperature is hotter in the core. So the core is dense because they think it's mostly nickel and iron, where we have silicates and stuff in the mantle and the crust. So the heavier stuff, because it's molten, the heavier stuff has fallen to the center. So the mantle is much less dense than the core. The mantle is rocky. The core is metallic, consisting of iron and nickel, which I just said. The outer core is liquid. The inner core is solid due to the pressure. Volcanic lava comes from the mantle, which allows us to analyze the composition of the mantle. Differentiation is, we talk about that a couple of times. It just means differences. So the variation in density and composition of our planetary material, so our planet is differentiated, not just a ball of the same type of rock. And this is because our planet was molten at one time, allowing the denser material to sink to the core. Radiation and leftover heat have allowed the core to remain hot, which also allows us to maintain our magnetic field, which protects us from the sun. All right, I think that's it. For that one. So surface activity on the Earth, summarize the evidence for continental drift and identify physical processes defining it. So continental drift was proposed and like completely rejected, I want to say in the 1920s. And then in the 60s, when they were able to like do some radar mapping of the ocean floors, they did actually find these mid-Atlantic ridges and other stuff. What happened is this dude looked at this and went, oh, look, that fits into there. They must have been the same thing at one time. So they must have drifted apart, continental drift. And people were like, ah, you're crazy. So anyway, so now we know though that there are plates, and at the boundaries of these plates, we have earthquakes and volcanoes. So if you look, I was actually in Chile I'm not sure when you're seeing this video, but I was in Chile recently and there were 2 earthquakes while I was there. There's also earth volcanoes. Mount St. Helens is up here. Of course, the San Andreas Fault is here. So, and if you'll notice, each of these plates have like arrows on them because they're moving in different directions. And like the Indian plate smashed into the Eurasian plate. Is that where it was? And there's like double plate thickness, and that's where the Himalayas are, kind of thing. Very strange. Okay, plates moving away from each other create rifts. So in the ocean, there's this convection cell in the mantle, and so this is sort of pulling this way, and this one is pulling that way, and so it makes this ridge, and it fills in with lava, and it pushes the plates farther. Also, we have some sinking plates, some subduction is what it's called, where this plate is smushed under this plate, and this is where you get volcanoes and stuff like that. So this leads us to the the dude who thought that there was continental drift. If we go backwards in time, then we had this. It was called Pangea, is what they think the original. Like there was just this big old landmass that then broke up and the plates drifted apart. And as I said, this guy noticed that South America sort of fits up into Africa. There's also this weird coal seam and mountains that continue from North America up into Europe. Kind of cool. So plate tectonics, they're slowly moving the plates. They cause earthquakes and volcanoes and mountain ranges. Okay. Surface of the moon is a little interesting, not as interesting as Earth, but so we'll describe how dynamic events early in the moon's history formed some of its major features. So the moon has large, dark, flat areas called maria. Early observers thought they were oceans, but we think they're now due to lava flow. So here is a picture of the Earth. And if we zoom in here, this is a mare, maria. And then if we zoom in again, we have some of these impact craters that we can see. The far side of the moon is heavily cratered with very few maria. The lunar highlands is here. It's a region that's sort of elevated above the maria. The Artemis team flew behind the Earth or behind the moon, and were able to see the backside of the moon in 2026. There you go. Okay, so craters are formed when a meteoroid strikes the moon. And the explosion then leaves behind a crater. So we got a meteoroid that smashes down, makes kind of an explosion, sends shock waves in the material. There's a big rebound, and then all the stuff is flown out on the side. And we have a crater left behind, and then all of this junk. So craters are typically about 10 times as wide as the meteoroid that created them, and they're twice as deep. So we can kind of measure how big the asteroid was that hit it. Rock is pulverized to a much greater depth. Most lunar craters date back to at least 3.9 billion years, we think. There's been much less bombardment since then. So we had this period where they think the solar system was 4.5 billion years old. We think that something hit the Earth, create the moon. I think we're going to have slides on that in a bit. And so they think that there was a whole bunch of stuff still flying around, and it sort of stopped about 3.9 billion years ago, that most of the junk kind of settled down. So meteoric impact is the only source of erosion on the moon, since there's no atmosphere and there's no rain. So there can be very large or very small craters. So there's a bug in here. So here is a very large crater, 30 kilometers across. And then of course there's some very small rocks that also have craters within them. If you come by the observatory and do any of our observing nights through the semesters, fall and spring semesters, we usually have them published and up on bulletin boards in McGill and in Rhodes. And we post them online. Sometimes we do specific things where we can see the moon and you can see the mountains on the moon, which is kind of cool. So regolith is this thick layer of dust left behind by meteor impacts. The moon is still being bombarded, but they're very small micrometeoroids, and it's still doing some erosion. So you can see how deep his footprints are because it's just this dusty stuff up there. Also, say real quick, the reason why there's no stars is because this is very bright. And so if you were to open the shutter on the camera in order to capture the stars, this would all be washed out and you would not see it. So it's an artifact of astronomy, of photography, sorry, that you have to take a faster exposure time in order to get the data here, but you lose the data here. If I were trying to keep the shutter open longer to get the stars, then this would be all washed out. It would just be white and you would see no details. So anyway, overexposed. So the magnetosphere, so the Earth has a magnetic field. And so this is the sun and the solar wind is hitting us. And so we have this comes out the south and goes into the north. And so we have these magnetic field lines. And because the solar wind is the solar wind, it sort of pushes it and it sort of gets this weird thingy tail out the end. And Jupiter's magnetic field lines are similar to this. And I think they actually extend past Saturn. So anyway, we like this. The magnetic field line protects us. There's these Van Allen belts that capture some of the ions from the sun and help them keep them out of stuff. When we get a solar storm with solar activity, and if it sends out a lot of charged particles and stuff, that's when we can see aurora. And in Southeast Missouri recently, we've had a couple of nights where you could see aurora. It's not actually a good thing when you could see it this far down because the Earth's magnetic field is weakening and moving a little bit. So anyway, near the poles, the Van Allen belts intersect with the atmosphere. The charged particles can collide with the atmospheric atoms, and then they glow a little bit, and then they can create aurora. And from here, when we see the aurora here, if it's depending on how far down you can see it, we're seeing it just in the upper atmosphere. So it's very low to the horizon. Your phone can actually see it better than your eyes can. Okay, so technically not part of our planet. The magnetic field, it's continuously generated by Earth's core, and it only exists because the core is rotating. So this dynamo theory describes the creation of planetary magnetic fields, rapid rotation, and blah, blah, blah. Okay. So anyway, because we have the solid core, the liquid thing, and it's moving, and the core travels, I think, a second or so faster than the mantle. So it's spinning a little bit faster. Anyway, we're able to create this magnetic field. The moon has no tectonic plate movement, no volcanoes anymore, and no magnetic field that has been detected. Okay, the history of the Earth Moon system. So the current theory is that we had a glancing impact by a Mars-sized body on a still liquid melted Earth that caused enough material, mostly from the mantle, to be ejected from the moon. This is a computer model of that. So the moon and Earth are dissimilar in density and composition, so they don't think they formed at the same time. But there are some similarities, mostly in the mantle. So here's the Earth and its young time. It got smashed by something. It kicked off a lot of stuff, which eventually coalesced into the moon. So nobody says what happened to the thing that smashed us. Did it? I mean, I guess it right here, it's all destroyed and everything, and then it created the moon. So anyway. So here is an estimate, a drawing of what we think the moon sort of looked like. So about 4 billion years ago, we think it had some impact craters, but no Maria. Then there was this period of volcanic activity where we got some Maria, and then here we are today. If you'll notice, some of these craters have lines coming out of them. That's the ejection stuff. So when something big hit it and it spewed out a whole bunch of stuff, and you can see a couple spots on there where the moon does that. So the moon most likely formed when a Mars-sized object hit Earth. The core of the impacting body remained behind as part of the core of our planet. Debris spattered into space and formed the moon. Lunar volcanism was stifled when the moon's mantle cooled. after extensive lava flows formed. So things change and it cooled and no more volcanoes on the moon. All right, that's it for chapter 5. Please email me if you have any questions. I hope you're having a wonderful day. Read your book. It's good for you to read your book. Okay, I'll talk to you later. Bye.